Good morning, everyone. So my name is Gerome Melaet. I've been a postdoc in the Summertime group for about 3 years. And during that time, I've been in charge of the Fischer-Tropsch project. In the group, we've been investigating different effects of nanoparticle support and composition on the product distribution of the Fischer-Tropsch reaction. So the first one we looked at was the cobalt nanoparticle size by using colloidal route to produce a well-controlled size of cobalt nanoparticle. And we can see that in this case we have an effect as the turnover frequency will increase with the size of nanoparticle. We also looked at the support effect. In this slide represents the effect of titanium dioxide, which was shown to be encapsulating the nanoparticle and decreasing the TOF. And recently we started to work on different bimetallic composition from cobalt copper, which is the one we present here, cobalt rhodium, cobalt rhenium, and other different systems to see how the composition would affect the product distribution. Those three studies are done in a Fischer-Tropsch reaction at steady state. So it's a high pressure reactor, and we wanted to go further away and try to get new insight on the mechanistic of the reaction. To do that, we came up with a new reactor, which the experimental concept is simply to induce perturbation to the system and observe that system going back to new equilibrium. To do such a thing, you need a time-resolved experiment. And the way we induce the perturbation could be by a fast change of the temperature, isotopic. Those working in Fischer-Tropsch are well familiar with CISCA experiment, or simply by a gas composition. It will give us mechanistic information that allow us for a better architecture of the catalyst and a control on the mechanism. In our case, we decided to do the gas composition. The way we do the experiment is simply by feeding the reactor with hydrogen and helium, and then switching really fast to a reaction condition, hydrogen and CO at atmospheric pressure. This means that we're looking at the first step of the reaction. We're looking at the buildup of the surface as we go into the reaction condition. So what happens when you switch to the reaction condition is you see the CO coming out of the reactor, and you have a time dependence of the product coming out of the reactor. This type of experiment need a few important factors that you have to control. The first thing is you need a fast data acquisition, which is lower than a second. The order of the time order for that switch is 60 seconds. After 60 seconds, you're already at steady state. You want also that all the phenomena, chemical phenomena that you observe are easily detectable, and that you have no problem with diffusion or filling up the reactor and all those things. So we designed a reactor with a small dead volume, and you don't want any change in the concentration as you go from the reactor all the way to the detecting system. So the rest of the reactor was designed to be a block field, so there's no change in concentration as we're going all the way to the detector. And the last thing you want is to be able to be inducing those perturbations really fast and in a reproducible manner. So to do that, we designed a reactor, and in front of the reactor, we have a full waveform that separates two circuits. Each circuit can be fed with a different gaseous composition. So circuit 1 would be hydrogen and helium. Circuit 2 would be hydrogen and CO. As we switch the valve, we can go from circuit 1 to the reactor directly to C2, so circuit 2 to the reactor. Behind the reactor, at the outlet, we're analyzing all the outlet flow through an online mass spec that is differential count. And then we have a system that allows us to sample in time and to be analyzed further on a different analytical system, which I introduced here. So you have the reactor, we have the continuous sampling using the online mass spec that is this one. And we have another system where we can do the sampling in a vacuum sealed flask, and we can analyze those flasks further later on a GCMs. The advantage of combining those two is that on the online mass spec we have the time dependence. We can see the product and the CU coming up and follow it in time with a resolution of 2 seconds. The resolution is given by the fact that we're looking at multiple ion detection mode in the mass spec. So the sampling rate of that one is 0.5 seconds. But because you're looking at 18 masses, different masses, to be able to draw a correct picture of what are the product coming out, we're limited to the 2 second resolution. In this case, the sampling, the volume you sample, and the speed of the flow will give you the time resolution. In our case, we have 1.3 millimeter sampling with flow at 40 SCCM. So the time resolution we have for each sample is 2 seconds. Alright? The advantage of the GCMS is that it's highly sensitive, way more than the online mass spec we can see in other products. The disadvantage is it takes just 45 minutes to do one sample to separate all the product we have. So to prove you that our new system works properly, we decided to compare our system to a system in a publication that is well known in the literature by Professor Cruz. They use a cobalt-manganese catalyst that we produce the same way. And we did the testing in the same condition. Here I'm showing you that their catalyst, the physical and chemical properties of it, are quite similar to the one we have. So we have the same range of particle size, the same range of BT. And if we look at the metallic surface area, which is done by chemisorption, we can see they're really close. The CO conversion at steady state, so after the buildup, when we wait for a few hours, is quite identical, and so is the TUF, because we have almost the same metallic surface area. Now, let me introduce you here the figure they presented in their paper. So this is the online mass spec. That's the signal you observe directly with the online mass spec directly after the reactor. You can see that they have a buildup of CO coming up and methane, and in this instead other products showing up. It's about the same for us. We have methane first, CO later, and then we have other products showing up. When we look at the delay time, which we define as the time between the switch and the time you observe the first few molecules coming up, we can see that they are quite similar for each range of molecule we detected at the mass spec. Unfortunately, with those systems, it is difficult to resolve molecule with a longer chain than C3. C4 and C5 at dose pressure are not easy to be seen. The concentration is so low that the mass spec doesn't pick them up. So what we did is, during the transient period, which is the buildup of the surface, we did a few sampling, so in the vacuum flask and into the GC, and we sampled them in the GC, and calculate the selectivity. What we see is mainly methane, as can be seen here in the online mass slide. But then, as the reaction progresses, we can see that not only we have C2, C3, but also C4, C5, and C6 coming at atmospheric pressure, which is already an interesting result in itself. All those longer chains are formed within 45 seconds after the switch, which means that before reaching the equilibrium, we have most of the longer chain already coming out of the surface. This is the daily time for those longer molecules, so it takes 20 to 47 for them to appear. The sequence we observe is we're forming a smaller chain and then it grows up, which is, I believe, expected. Now, the other important thing is when you have those molecules, you can have unsaturated product, saturated product. For larger molecules like C4, you can have different isomer. And so our online mass spec cannot really differentiate and account for all those molecules, just because fragmentation is so complex. Even if you're looking at 18 or 19 mass over charge ratio, you're not able to resolve everything. Whereas with the GC, it comes really handy. You separate them, and then we have a mass spec, and we can pinpoint what molecule we have. So that's what we did. And I looked at first the ratio of olefin to paraffin, because this one is quite simple. And you can see that in the first few seconds, we don't produce any unsaturated molecule. You have to wait 35 to 40 seconds to see the first unsaturated molecule. Also, we look at the probability of branching. So I looked at the amount of branch molecule we produce, and we normalize it into the number of linear molecules, C4 linear, C5 linear, and branch molecule for C4 and C5. And what we observe is that you have drastic increase in the probability. It's still very low, the selectivity is really low, but here you have a change. You first form a branch molecule before you form the unsaturated molecule. So this indicates a change of distribution. Now, what I want to look at is the big picture. And the big picture is this one. So if I look at the selectivity for the linear, which is the same as if I look at this selectivity at the mass level, and then I combine it with those two graphs to get an idea of what's going on, we can observe that at first we have the branch. When the branch starts decreasing, we have the unsaturated molecule coming out. And at the same time, the first few molecules we're producing are only linear. Once you reach the steady state, those conditions are quite similar to a regular cobalt catalyst. They are the selectivity that you observe for 1 bar atmospheric pressure cobalt catalyst. Now, I'm going to make it a little bit more complex, but that's where it got interesting. What I looked also is the coverage of carbon. So I simply calculated what I put in as carbon, what comes out at a mass spec, and what comes out as product. And the difference of all that, I normalize it to the surface of cobalt. And what you can see is that in the first few seconds after the switch, we have no carbon deposition at the surface. Every carbon coming in at that low pressure will be reactive. Mainly it will react to methane, and that is what we see in this one. You can see that it's mostly methane, so we have that methane peak. But once you start accumulating carbon at the surface, that's where you start forming a branch, which is, it's longer molecules. So, of course, if you have an accumulation of carbon at the surface, you're starting the polymerization of the surface. Once you reach a certain value of that coverage, it's where you can imagine a steric effect. So you have so much carbon at the surface that the branches are not favored at that point. It's difficult for them to be produced, and you start producing desaturated. It's worth noticing that both branched and unsaturated molecules that I observe are only the termination one order, the first C1 to C2 carbon, which made me think that this is a steric effect. Imagine if you have, in the first few seconds, you have enough surface to have the branch, very few branches produced at the surface. As you increase the carbon, you increase the number of polymerization channels, and you have less possibility to have the branch. You're forming long chains that are easier terminated by an unsaturation than by a branching. So right now, the conclusion I want to take from this talk is simply that the GCMS with the online MS give us further information that are not obtainable with the online MS alone. It can give us useful information on the mechanism. For example, we can see that the growth sequence is C2, C3, C4, C5, like I presented earlier. We also saw that the product distribution changed drastically from the branch to the unsaturated. And right now what we're trying to do is to improve the measurement of hydrogen and oxygen, simply because water has a chromatographic effect. So if you're looking at time resolved experiments, the water will show up later. And so it's difficult to quantify hydrogen and oxygen, especially oxygen, but it's difficult to quantify and to calculate the correct coverage of the surface. And finally, we'd like to move to a modal catalyst, because the cobalt manganese that we've been using is anisotrope. We don't know the structure of it. The particle average is 34 nanometers, but you have larger crystals and smaller crystals, so it's difficult to evaluate what are the facets. So we'd like to use more nanoparticle and our knowledge in nanoparticle to obtain more insight in the mechanism. Finally, I'd like to thank Professor Samajai for having me in this group, the two grad students working with me, as well as doctors working and advising me on how to do those reactions. And I'd like to thank you for your attention.
Thank you very much. Questions? Slide number 14, you calculated the coverage with carbon, so you gave arbitrary units, but what's the order of magnitude that you arrive at, and how does it compare to Sitka measurements, for example, and done through Professor Holman? What are the numbers?
So the number I've got here, and well, taking account that I only normalized it to CO surface atom, I don't know the hydrogen or the oxygen. I've got here a maximum of 3 carbon per surface cobalt.
3 carbon?
3 carbon per surface.
So much more than the steady state value of reactive carbon.
It's even more, actually, because if you take into account hydrogen and oxygen, then you have less surface atom.
Yeah.
No, the thing is, this measurement gave me...
So this suggests that this carbon is used in the development of your particle.
It might. You can also, from that measurement, it's not an absolute measurement of the carbon at the surface. What I'm doing is, I know how much I put in. It's a mass balance. So if you imagine a longer chain growing polymerization being going on. So you might have carbon stacking up and not one surface carbon per surface atom. So it might be diffusion in bulk, but I have at this point no information to confirm or go the other way.
Yes? But we can probably do some statistics on this, right? Because your chains go up to C4, C5. By the way, it's nice work. So if you then just assume, probably should, that means that the average species on the surface is less than C2. So that makes it very hard to come to a carbon to cobalt ratio of 3.
Yes.
On the other hand,
no,
you have a support, right?
Yeah.
Carbon can also go to that support.
Exactly. So that's why I was saying at the end, we'd like to go to a more model catalyst where we control all the parameters of the catalyst, simply to simplify the problem and maybe input TFT calculation to try to model